Yeah, so Gonzalo forced me to give a title, so sorry, this was not great. Anyway, okay, so I'll talk about some questions, thoughts, and workshop goals with examples of work done by Stony Brook members. So so usually I don't prepare much ahead of a workshop unless it's a workshop I'm organizing. But actually, for this one, last week, I sat down for 2 hours or so with Jared, Aditya, and Aaron, our 3 Pheno postdocs, and we thought about, what the workshop goals should be or what we can contribute. So I don't know if anything useful came out of that, and only a fraction of it made it in here, and they haven't seen the actual talk, so I don't know if they agree with everything, but anyway, we try to think ahead a little bit. Okay, so first, actually, the organizer originally asked me to give a talk on an overview of models. So I didn't really want to do that, and David said it's okay not to, but here's my one slide talk summary on on some of the models that are out there. But the question really for the workshop is, can and even should all these be captured with just a few benchmark models, right? Can we abstract actually the essential things from this whole range of physics that is in principle possible for the dark sector? And also, maybe some of them are more interesting. So those are the kind of questions I think that we have to ask in this workshop. Now, for the workshop goals, we want to identify, that's from the website, right? We want to identify dark matter benchmark models representative of qualitatively different astrophysical phenomena, and then also coordinate the development of simulation tools that will allow for detailed astrophysical predictions. So as part of this, right, or maybe sort of as a separate thing also, I think some of the discussion should also perhaps go into the following. What can and what should be studied first with semi-analytic methods before doing n-body sims? And then a related question, how can theorists like myself contribute, and what other theory work is necessary before we embark on detailed n-body sims for a lot of the work? So maybe you also heard this in the previous talk from Kim, but maybe, and Simeon mentioned it this morning, maybe the theorists are just scared of n-body simulations, but I think there's actually a lot of stuff we can do without doing the full n-body simulations. And then a related question, which is related to the second point up here, what systems should be simulated? What's really the most important thing, especially also in relation to what Addison raised this morning? Where can we be sure that it's not just baryonic physics that might be mimicking the dark sector? What can we actually simulate where we can get real information and differences between CDM and baryons with non-CDM and baryons? And then also what simulation outputs are needed. So I will just discuss a few, that's sort of organizing my talk, these 3 bullet points. I want to attempt to address these 3 aspects in detail. We already heard a lot of examples earlier today from the other talks, but I'll just present some examples of this from work done by Stony Brook members, not just by myself, but also by others, and of course also often in collaboration with other people outside Stony Brook. So let's start with what can and should be studied with semi-analytic methods before doing n-body sims, and I'll just give some example. So first of all, before we simulate in detail, I think many things can be understood with semi-analytic methods. They are easy, they are fast, they're useful in the sense that they give intuition. You can generate large statistics, you can easily vary your input model parameter. So it's very useful to do that rather than running an expensive n-body sim for a particular point. It's very useful for non-CDM, as we already heard, but even, since it's easy to scan parameters, but even within CDM, these approaches are still useful. And of course, later on, once you understand the parameter space a bit better, you can do this, you can verify this with more detailed simulations. So I'll just give 2 examples. First one is what we've done is we've looked at the impact of CDM subhalos on globular cluster stellar streams. And then I'll mention work by Aaron and collaborators on SIDM subhalo distributions versus Milky Way satellite data. So one thing we are looking at, and this is led by my student Duncan Adams and a postdoc DJ Parikh and Aaron Sloan as well, and then some older people. So what we're looking at is we're trying to understand the impact of subhalos in CDM on globular cluster stellar streams. And the idea is where we want to do this, and then we can, of course, extend this with non-CDM models as well. But what we're doing is we're using a semi-analytic model called SatGen, satellite generator, to generate many realizations of subhalo distributions for a Milky Way-like galaxy. Then we include a model of a GD1-like stellar stream to quantify sort of the typical distributions of the stream subhalo encounters. And we model those encounters with a program called Galah, which was written by Adrian, who's one of our co-authors as well. Now, the nice thing about SatGen is that it combines dark matter halo merger trees, analytic prescriptions for various things, like it does orbit integration, tidal stripping, dynamical friction. So it's a very good emulator of, presumably the real thing. and it's very fast to do compared to full simulation. So it's fast and allows for large statistics studies. And I think this is important for predicting stream features in this case, and can answer, for example, how likely is it that subhalos create the observed GD1 features. So just as an example of what one of these impacts looks like, so here's a histogram of the density of the number of particles along the stream. Phi1 is the coordinate along the stream. Here's an unperturbed stream. There's a progenitor here. And then the perturbed stream, so clearly you see a difference. And then you can look for these kind of little gaps. They have some width and some depth that you can try to fit for. And this, of course, is a particular, impressive, in one particular visualization, is a particularly impressive encounter. And then you can try to understand the distribution of these subhalo encounters. So you can look for how, and you can make distributions of these. So here's just a preliminary set of plots that Duncan made, where we look at some of these distributions. So for example, you can look at the stream subhalo impact parameter. We can look at the relative velocity of the stream and the subhalo at impact. So what sort of gives the most important things, how close do they have to get, how close do they typically get, and then the width of the gap and the depth of the gap sort of just fitting a little function to the diagram that I showed on the previous slide. And then you can look at these distributions, and then maybe you'll learn something, right? You can learn what are sort of the typical relative velocities that happen. There's other parameters that we have that I'm not showing here that you can look at. What is the typical mass of the subhalos that create these encounters? So this is a work in progress, but hopefully it'll be out in sort of a month or so. And we will, and I think this is sort of one study. And then, of course, you can build on this. You can do what, there's a nice paper that Joe mentioned this morning with his work with Bannock and others, where you can look at sort of the small impacts and look at the fluctuations in the GD1 stream, where you don't look at just a big impact, but to the accumulation of many smaller impacts. Okay. Another example that I want to mention, this is from Oren, so I'm not involved in this work, but he made this nice plot, and this is work to appear with these people here. So what he's looking at is the subhalo distribution within SIDM, just using various prescription to try and calculate what the subhalo distribution looks at, including gravithermal collapse, tidal stripping, etc. And then he's asking the question, what is the, as a function, so on the y-axis here, I'm showing the sort of a typical radius, like the half-light radius, for example, and then the mass enclosed within that radius. And what you see in the colored curve and these contours are where most of the PDF is peaking, where most of these subhalos lie. So we see a lot of them lie here, but then you see as you go to this region that there's sort of two populations, and in particular, the ones that seem to have very low enclosed mass, those are subhalos that are in the core expansion phase for this particular self-inducting cross-section with a particular ratio of the mediator mass over the dark matter mass. And these will then show up sort of as having a lower M half value than some of the other subhalos. And on the other hand, you have subhalos that have been gravithermally collapsed already, and you get this bifurcation a little bit. So that's a prediction that's based on their modeling. And then you can compare this with Milky Way data, which are in green. And for this particular parameter point, you see that it doesn't disagree. And then you can say, okay, this is ruled out. Okay. And of course, you can do this for other parameters. You can do this very simply because it allows you to, you're able to scan very simply over these parameters. And then one thing you can do is, of course, say, okay, for particular points, we can check this with SIDM n-body simulations. So that's one thing that we started looking at. Can you actually see this effect from that sort of predicted in actual simulations? Okay. So those are some examples. Okay. Then I want to mention very briefly some theoretical work. So in particular, I want to mention our dissipative dark matter as an example, where we've some work that's been done already and some work that's been going on. So we've heard a lot about dissipative dark matter. We have a very nice talk already on this, and so people mention it. So I'm not going to spend too much time, but basically dissipative dark matter, one example is atomic dark matter, very nice example. It consists of dark electron and a dark proton and a massless dark photon. It's motivated by naturalness, as we heard about. There's 5 parameters, so the fraction of the dark matter, of the atomic dark matter to the total dark matter, the fine structure constant of the dark sector, the electron mass and the dark proton mass, and then some temperature in the dark sector, or Xc, depending on how you want to parameterize this. And there's been many existing studies, and we had a nice talk earlier today by Caleb about this. Now, for a lot of these studies, you need various ionization rates, you need various recombination and cooling rates, and those can be rescaled from standard model rates for fine structure constants that are very small, so sort of the order alpha electromagnetic, the fine structure constant, and the electromagnetic one. And of course, you can go a little bit higher, of course, away from this. And they're used for dark electron masses that are much less than the dark proton mass. And there's very nice code, like we heard about darkroom a little bit, and Sarah and others have done very nice work on this. So one thing we're doing is we are trying to do this actually for the general, we're trying to get these rates for arbitrary alpha dark, sort of for in the general atomic dark, get these general atomic dark matter rates, where we derive them from first principles. So we want to sort of do this for arbitrary alpha dark, and also for arbitrary electron, dark proton masses. In particular, not just assuming that alpha dark is small, but trying to get as much close to 1 as possible. You can't get all the way to 1. At some point, you have to include relativistic effects. And then also for arbitrary dark electron, dark proton masses. And the hope is that this can then be used by, to extend some of the previous studies. So I will not discuss these equations in detail. I'm just going to, this is a work in progress, led by two of my students and also Jared Barron, he was here. It gets quite complicated, but it's just quantum mechanics, right? It's actually not, in principle, it's very simple, but trying to actually solve this, it gets quite complicated. But just looking at, for example, the phonization and recombination rates, you need to calculate some overlaps for some initial and final state. There's some quantity sigma tilde that you can define. Only one of these appears in the standard model and only in a dipole approximation. But in principle, you've got to include these higher order, these other terms. And if you want to sort of extend this parameter space away from the standard model approximations, equations get complicated. I'm not going to discuss them in detail. They're numerically quite annoying to solve, but you can do it. And then just one example is that, so far what we've done, we've confirmed, for example, that the exact recombination coefficient, so going from sort of a continuum state down to the n equals 2 state, the 2,1 state, that matches with the value from the standard model. We're keeping, in this particular example, we're still keeping alpha dark small to be the electromagnetic fine structure constant, but we're taking the dark electron mass to be the electron mass, so 1 MeV, half an MeV, and then varying the proton mass all the way from the GeV down to an electron mass. And the exact curve in blue, that's our exact calculation, and the scale standard model rate, which has some simple scaling, matches this one very well. Okay, so that's just one thing just to confirm that the code is sort of working and it's doing what we wanted to do. And of course, now the idea is to try and extend this for the wider parameter space, also for larger alpha dark. But that's one thing that maybe is useful to, given how much attention atomic dark matter is getting, this may be useful for extending the, sort of looking at the fuller model. Yeah.
This is very cool. Should I be surprised that scaling works all the way up to essentially degeneracy?
So, in hindsight, you never know. So we were a bit annoyed by this. I will admit it, that it works so well. I will not lie. So, but on the other hand, things, of course, are known for positronium, right? Electron, proton. Electron and positron. And it was known apparently that this, I didn't know it, but one of our collaborators, Jesus Perez Rios, he's an atomic physicist. He loves molecules and atoms for some reason, but he said this is known for, this was known that positronium does actually work for the scaling. Okay. Yeah, so this is annoying, but it is what it is. Okay, so we confirm stuff. Okay. Now, another thing I want to mention is we heard a lot about atomic dark matter, but there's actually, I think, a much simpler distributive dark matter model. And we've looked at this in 2018, and this is in a paper that Jay Hawk and Daniel Ogrinovich was on, and Chris Kovaris. And this model is much simpler than, well, a little bit simpler than atomic dark matter. It consists of a dark electron and a massive dark photon, okay? Only 2 particles. And there's no bound states, which is beautiful, unless you are an atomic physicist or unless you're a lot of you people like. Anyway, okay, it's much simpler. So it turns out that this can also form non-trivial structure, which we try to predict using a very simple analysis. There's 5 parameters again. So it's like this, in that sense, is the same as the atomic dark matter model. Instead of having a dark proton mass, which we don't as we had in atomic dark matter. Here we've got a dark photon mass, so that's sort of the one parameter that's different. But having no bound states helps with analyzing it. And you can choose these parameters to make sure, I'm not writing down the conditions, but you can derive these conditions, in them to make sure that you have galactic size perturbations that grow gravitationally, and then they become nonlinear. And that also the dark electrons decouple from the dark photons before matter domination. So we want to set that up. And the idea then is to try and look at what kind of exotic compact objects can we form in this very simple dark sector. Okay, so there's some conditions on these parameters, which I didn't write down, but one can derive them. And that's also what we did. And then once you start forming this, you decouple from the Hubble flow, you look at a certain perturbation, let's say a Milky Way size perturbation, and then you start having a cloud of these dark electrons, and they can start collapsing, and they can fragment because there's Bremsstrahlung cooling. So, and they can fragment into halos of size of the solar mass to 10 to the 6 solar masses. So it's just the simple interaction that gives you the cooling. So the dark electrons can scatter over themselves and emit a light dark photon. We make the dark photon light so that we can emit this. And then in this analysis, we begin from the growth of the dark electron overdensities in the linear regime. Then we study the growth of these perturbations in the nonlinear regime on galactic scales, because we want to sort of do this for a Milky Way size scale. And we look at the fragmentation of the halo due to cooling. And we use a genes analysis. And this analysis, it was analogous to analysis that was done by the Rouven sector by some seminal papers in the 70s. Okay. And in this simple model, what we find is the following. So I want you to ignore most of the lines, well, most of the stuff. Here's the dark photon mass. Here's the dark electron mass. So going from an MeV to a TeV. Dark photon mass goes from 10⁻³ eV up to 10⁵ eV. This is, can't see the color so well. Anyway, okay, so ignore these little bands and so on. But what you can see here this is supposed to be black. This is the mass of the exotic compact object that forms. This is 100 solar masses. This is 1 solar mass, 10 to the 4. 10 to the 6, and so on. So you see a big range. And then in blue here is the compactness. So this is a compactness of 0.1. That's a compactness of 0.5. Everything above here would be a black hole. Here is a 0.1. So a neutron star is about 0.1, 0.2 or so. The sun is about 10⁻⁶. So you can even get solar compact objects that are sort of have the density of compactness of that the sun has. In this parameter space. And this is for a particular choice of alpha dark. And of course, you can easily vary over that and see what you get. So it's a very simple model, but even in a simple model, you have a large range of exotic compact objects that are possible. Now, it would be nice to follow this up with numerical simulations. In some ways, it should be much simpler than the atomic dark matter simulations that have been done. But this is a model where you have where you can get a lot of intuition from the theory here and see if it actually matches with what you might get from the simulations. Or maybe this model will also destroy your Milky Ways, like we saw in simulations that you guys have done, right? Okay. Now, there's related analysis for atomic dark matter in this paper with the two Sarahs and Gurian here. And also, there was a paper earlier this year, for a model with early matter domination, where they did a sort of a similar type of analysis to look for exotic compact objects. But there's, these are sort of nice models, I think, where in this case, you have a lot of control, theoretical control, and you can try and see what comes out of it and make predictions for observables as well. Okay, so that's just two examples where some theory work may be useful or not for the topic of the workshop. Okay, so then the last thing I want to mention is what systems should be simulated and what simulation outputs are needed. So of course, there's lots of things one can talk about, but I want to mention, it depends really on the observable and the probe, and I'm sure we'll discuss this. But here I want to discuss one powerful probe and what is needed to make predictions for it. In particular, sort of what is the output, what simulation outputs are needed in order to make predictions for this. And that's CMB lensing on small scales. So again, this is not my work, but it's work that's being pushed by Nanima Sehgal, Stony, Brook, and collaborators. And the idea is that instead of strong gravitational lensing or weak lensing, you actually use the CMB as a backlight that's being lensed by the intervening matter. So this directly probes the total matter distribution without relying on baryonic traces, which is great about lensing in general, of course. But the nice thing about this using the CMB is that it has a well-known redshift and has its intrinsic properties are very well understood. Now, there's a proposal called CMB HD, which is a low noise, high resolution millimeter wave survey over half the sky. It's proposed to be have 6 times higher resolution and 3 times lower noise than the CMB S4 wide area survey. It will measure angular scales out to 40,000 in L. It's located in the Atacama Desert in Chile, and it has 77 frequency channels, which will help you to clean foregrounds, which are going to be an issue, but you can deal with it with these various frequency channels. And there's papers for the Astro 2020 decade, although there's a SNOMES 2021 CMB HD white paper that was put out if you want more details. So the collaboration has about, I don't quite know, but maybe 70-ish or so, and growing a number of people. So CMB HD lensing, so CMB HD really tries to push lensing to a sort of a new, quantitatively new frontier. And it can probe the matter power spectrum to scales K of about 55 H inverse megaparsec, which corresponds to halo masses of about 10 to the 8 solar masses. Here's a plot of the matter power spectrum. So you see a lot of previous data on it as well. And then here's the forecasted sensitivity of CMB HD in red here. And here you see the fractional error. So sigma, the error on the power spectrum divided by the power spectrum as a function of the scale. So it really goes to sort of for these kind of observations, goes to a qualitatively new regime. Now, we heard earlier about, Caitlin mentioned about transfer functions, right? So those came up in the discussion previously. So what we really want to do is to have the nonlinear transfer function, okay? So if you have some model, and I'll give you one example here. So here, you can study models that suppress small-scale structure by applying a transfer function to the CDM, nonlinear CDM power spectrum, matter power spectrum. And the nice thing is that, in principle, there's no reason why the dark matter model and the baryon should affect all the scales the same way. In particular, there is a paper here by Mead et al., which Nalima and her student Amanda McGinnis used in a paper earlier this year, where they used that, and they are showing the transfer function for baryons with CDM and just over pure CDM. And you see that they affect, this is a function of redshift, so the color coding is redshift. And you see that baryon feedback has, you see the impact that the baryon feedback has, basically, as a function of K. Here is warm dark matter, just taking it as one example. So this is a 1 keV warm dark matter particle, which is disfavored from various other reasons, but just to show sort of the impact. And you see that warm dark matter also gives you, affects gives you a different transfer function. And again, it's color coded by redshift, but the point is also that it affects it differently on different scales. So the idea is then to try that you can constrain, in this case, warm dark matter by just measuring out to these high scales that CMB HD can probe. Now, this is just one example. And what we really would want, this goes back to the workshop question, like what is some of the outputs that people want for to constrain alternate dark matter models. And what would be needed for this probe is that you would want to make available the nonlinear matter power spectrum. So in particular, the nonlinear matter power spectrum, so as a function of K and Z, for Z range from about 0 to 15. And at 15, you really wanted to see, of course, that it goes back to the linear power spectrum. And this should be doable if you take your simulation output from whatever model you have and you just calculate the power spectrum. You just take the power spectrum. And I think that's a useful output, because then once you have that, then you can apply, to sort of make forecasts for, in this case, CMB HD. And there's a public forecasting code for CMB HD, which Nalima and Amanda made available at this link here. So that's one example for an output that will be useful to mention, I think, in this white paper that I think we're supposed to write. Okay, summary. I'm not going to go through this again. Yeah, that's it. Thank you.